So I will be talking about absolutely maximally entangled states. What you know for sure are maximally entangled states. So these are bipartite states of qubits or higher dimensional systems, QDs, which are in a pure state, and the reduced density matrix of each subsystem is maximally mixed. So it is proportional to identity. So a new concept is the word absolute. What does it mean that a state is absolutely maximally entangled? These are states which are not necessarily bipartite, but these are multipartite entangled states. I will give you an example, and they have the following property. If you divide particles from the state into two disjoint subsets, and you calculate the entanglement between one set of particles and another set of particles, so for this bipartition, this entanglement will be maximal. And it is for every possible division of particles in two subsets you can imagine. So it is not sure that such states exist, except maybe some trivial example. So here is the definition, and here is one set B, here is one set A. So this set consists in general of m qubits, particles with d orthogonal states. This set consists of some larger sets of qubits, and to be maximally entangled for this bipartite cut, they must be satisfied the following conditions. They are equivalent. So one is that the entropy is m log d, or density matrix is maximally mixed matrix of d qubits. So here, or the state can be written in such a form. These states were discovered by these people in 2012. So what they showed that these states can be useful for two quantum information tasks. One task is the so-called parallel teleportation, which some sets of parties can teleport quantum systems to other parties, and the other thing is quantum secret sharing. So let me give you examples. So the first example is trivial. This is two-partite state, so it is maximally entangled. So there is only one bipartite cut, so it is absolutely maximally entangled. The other example is also simple, but it is a good example to see what are absolutely maximally entangled states. If I will divide this state into this qubit and these two qubits, then the reduced density matrix will be proportional for the identity for this qubit. So this state is maximally entangled. If I will divide, for example, into these two qubits, and here it is also maximally entangled in this cut, so it is, and I can divide into these qubits and this versus this qubit in the middle. It is also maximally entangled, so it is absolutely maximally entangled. For 4-qubit absolutely maximally entangled states do not exist. So the next example is 5-qubit absolutely maximally entangled states, and such state was found. It is given by the following equation. There is also another state. It is given by such an equation. Here should be unity. This is called 0L or 1L because these are logical 0 and logical 1 of 5-qubit error correction code. So it is the most efficient call which corrects an error on a single qubit. There are also 6 qubits maximally entangled, right? So it is this qubit entangled with logical 0 and this qubit entangled with logical 1. And that's all we know about qubits. There are no more absolutely maximally entangled states of qubits. So for 7 qubits, you do not have absolutely maximally entangled states, and so on and so on. However, there are many states which are absolutely maximally entangled for higher dimensional Hilbert systems, and you can find in the internet the whole list of these states. Now I would like to tell you something about error correction, because that is the topic of this colloquium. So I will need stabilizer formally, so I quickly remind you what it is. Suppose I have a qubit and I will encode this qubit into such a repetition code. This code corrects a single error, but only X error. It doesn't correct Z error. You can look at it. This state is the following. It is superposition of 3 zeros and superpositions of 3 ones. So it is good to define the so-called stabilizers. So when you measure such an operator on this state, it is certainly equal to unity. Here you have 1 times 1, and here you have -1 times -1, so the eigenvalue is unity for this stabilizer, and the eigenvalue for this stabilizer is unity. And that specifies all possible states which you have. So states of this form live in 2-dimensional subspace of tensor product of 3 qubit Hilbert spaces. And it is called the code space. If an error occurs on a single qubit, you can measure the stabilizers, and you see that one of the stabilizers will have eigenvalues minus unity. So this tells you, the measurement of the stabilizers tells you which qubit you should correct. Okay, so for example, if an error happened here, we have here eigenvalue 1, here we have eigenvalue -1, and here we apply X3 operators which corrects it. You can define for this error correcting calls as logical operators. So these are operators which you should apply to the state to turn it into another state, for example, to perform logical bit flip. You just bit flip every of these qubits. If you want to change the phase between these two, you will apply this operator. So these are called logical operators. This is a simple example, much more difficult example, which was the first examples of a full error correcting calls which corrects an error on a single qubit was discovered by Peter Shaw. The state is encoded in such a way, and this space in which our logical qubit lives can be characterized in the following way, that you give the following 8 stabilizers, and it is a subspace for which all stabilizers has eigenvalue 1. If an error will occur, that it will go to some orthogonal change, that is, it changes eigenvalue of at least 1 stabilizer, maybe more stabilizers. Okay, and measuring stabilizers, you can correct this. So here it is how you do it. And here I have given you also the logical operators. So now I would like to go to absolutely maximally entangled states and stabilizers. Okay, so in general, I will be interested in qubits. So let S be abelian subgroup of the Pauli groups. I will tell you in a moment what is Pauli group, and we can define some state phi, which is a state with eigenvalue equal to unity of all elements of S. The Pauli group is generated by the following operators. So there is x to the power aj and zj to the power bj times some factor omega c. These are generalized X operators for QDs. And for example, you can give generators of this group and find a state as an state which is a state with eigenvalue unity for all operators. Sometimes this set describes higher dimensional state, such as we had in this, for example, repetition code or code short. Simply the set S is smaller. You don't give as many generators as you can. So you give smaller number of generators and they will be much more states which are with eigenvalue 1. Such a space we call a code, and the dimension of this code is given by n minus the number of elements of these generators. Here we have some operators which are logical operators. They commute with the set S, and here we have the logical qubits because the dimension of this logical Hilbert space is d to the power of d small to the power of d big. Okay, it happens that there are absolutely maximally entangled states, QD states, which are stabilizer states. And such a states can be mapped to a graph state. A graph state is defined in the following way. The generators of the stabilizer group for this graph state are equal to this generalized Pauli matrix xi. So for generator first we will have x1, for generator 2 we will have only x2, and so on, times the product of z operators for QDs from j equal to 1 to n to some power. I will give you in a moment a simple example so you will see how they look. This is the adjacency matrix. So this is adjacency matrix of the weighted graph, whose elements are 0 and d minus 1, and the diagonal elements are 0. So now I would like to construct from this AME state an error correcting code. So here is a formal algorithm. It may be a bit complicated, but in a moment I will give you a simple example and show how it works. So the algorithm is the following. Take the first m rows of this adjacency matrix A. Truncate them to their last n minus m entries. Form a matrix of them. The rows of matrix are linearly independent in this group, and then use Gauss-Jordan elimination to bring the matrix to a reduced low echelon form. Reduced low echelon form is the following form of the matrix. All rows having only 0 entries as at the bottom. Here you have examples of such a matrix. So here are zeros. The leading entry of every no-zero is 1 and is on the right of the leading entry of every row above. So here you have this. For example, in the first row, you have unity at the first position, and in the second row, you have unity at the second position, and you see that in the second row, this unity is to the right of this unity in the first row. And each column containing unity has 0 in all its other entries. So you see here are these columns. So now let me illustrate the steps of the algorithm. So here how our matrix looks. Here are number of qubits, and here are number of generators. Because the number of generator is equal to n, and there is n number of qubits. I will talk about qubits because everything we know is about qubits, and it is easy to imagine this. So this defines a state. So first, what we do is we truncate this to this first generators, and then use Gaussian eliminator to bring this matrix into low echelon form. So when there is in adjacency matrix unity, this means that we have Z operator in the appropriate generator, and we see here we have Z operator, and in the row below, we have Z operator to the right of the leading Z operator here, and so on and so on. So this is the first step of the algorithm. Now the second step of the algorithm is swap columns to the m columns containing only one unity to the last m positions. So by swapping these columns which we have here, we swap this to the position which have Z here on the diagonal. The first step is swap rows from m plus 1 to n in such a way that x appears on the diagonal, and this means that you reorder this matrix into this form. And this is almost what we want. We multiply the last n minus m generators by the first m generators in order to remove z's from the last positions of the last n minus m generators. So here are some z operators in these positions, and if you multiply this by these operators, this will be z to the power of 2. It will give us unity, and we move this matrix into this form. Now let me show what it looks like. It defines an error-correcting codes on these qubits from this position to this position. Let me look why. This acts trivially on the last qubit, so we don't have to worry. So we can think about it as the generators for the code which is described by the subspace of this many qubit space. These operators, these generators, of course, commute because at the beginning they commuted. So we have something like this, because here it is Z and here it is Z, this anti-commutes. So this part has also anti-commute. So it looks like we have logical Z operator here, and here we have logical X operator, so for one logical qubit. Here we have another Z operator for another logical qubit and another X operators. So in this case, we just have a code which encodes 3 logical qubits. Here it is summarized what I just told you. And here is an example. So here we have 6-qubit AME state. We bring it to this form, and we can look at the following way. Let us suppose that we would like to encode a single qubit. So we think about this operator and this operator as logical operators, but we truncate it to the 5 qubits. So we encode in 5-qubit error correction code. And this will be generators of this 5-qubit error correction code. Here it is given an example. So here are logical operators, and here are generators. We can also look in another way. We can think about this, that we encode 2 qubits. For example, here we have one logical operator. Here is another logical operator for first encoded qubit. And here is one logical operator for the second encoded qubit and one logical operator also for second encoded qubits. This will be generators. So this code encodes 2 qubits in 4 physical qubits. Of course, you cannot correct all errors, but only some set of errors. And you can also encode 3 qubits in 3 qubits, which is rather trivial. This will be logical operators for 1 qubit, for the second, for the third. So here is for the first, second, and for the fourth. Okay, here are just given the appropriate generators and logical operators for these all possible encodings.
So I'm saying that, starting with basically some graph state, which is related to absolutely maximally entangled state, you are doing this matrix operations so that you can get any, not any, but allowed n k, whatever distance we are not talking about, quantum error correcting code, stabilizers, as well as the logical operators.
Yes. Yes, but you don't have to. If you think about ground state, you should also have some Hamiltonian. So I think you should form Hamiltonian from these stabilizers, such as, for example, in a Kitaev code, Kitaev code. So in Kitaev code, you have these placket operators, and these are your generators of your error correcting code. And then you form Hamiltonian as a sum of different stabilizers with appropriate weights. And then if our eigenvalues are to unity, the eigenvalue of the Hamiltonian will be the smallest. Here I don't talk about Hamiltonian. So in order to talk about ground state, I would have to form Hamiltonian from these generators.
Why do did you start with 6 qubit absolutely maximally entangled state to get 5 qubit code?
Yes.
And why can't one start with some other? Is the choice unique or
Because they're very involved questions. So can you ask after the?
I can answer.
Oh, okay, fine. Yeah,
okay. So could you repeat?
So you started with 6 qubit absolutely
yes
state, and from that you get a 5 qubit code. Is this unique option, or one can started with 5 qubit?
Yes, and you obtain 4 qubit state, so you can have. So you can start from any absolutely maximally entangled stabilizer state. So which is described by stabilizer. So it is called in general for. So it is done in general for qubits under the condition that the d is prime, the dimension of the qubit. Okay, you can also start from the 6 qubit. Absolutely maximally entangled state and construct a code which encodes 2 qubits into 4 qubits. But of course, you cannot correct all possible errors, only some subset of errors. Does it answer your question?
Partially.
The other thing I would like to talk is how to find concatenated code. So sometimes you use concatenation of a code. So you encode a single qubit, for example, into 9 qubits. And then from this 9 qubits, each qubit you also encode in some error correction codes, for example, 5 qubit correction code, and so on and so on. You do this because this protects better from the errors. So here I will give you an example from entanglement theory about concatenation of codes. So let me first show you how to update the list of generators if there is performed some measurement of a state. So if the measured observable can be constructed from the generators, then we do not need to update the list. If the measured observable cannot be constructed as a product of generators, but commutes with all of them, then we add it to the list of generators with a phase factor depending on the measurement outcome. And finally, if the measured observables cannot be constructed as a product of generator and does not commute with some number of generator, then it replaces one generator with which it does not commute, while we multiply the other commuting generators by the generators that we removed from the list. So let us suppose that I have two states. One of states is absolutely maximally entangled state. Each stabilizer of the L state, L stands for left, can be represented in the following form. So on the last qubit is just simple Pauli matrix, and here are other qubits. And each stabilizer of the state R is of the form, so here you have some Pauli matrix, there are another matrices on another qubits. Let us perform an entanglement swapping on this state. So entanglement swapping is projection on Bell state. So think about qubits because it is simple. So Bell state is described by the following stabilizer. There is XX and ZZ. These are Pauli matrices. And it is an eigenstate of these two observables with eigenvalues equal to unity. So now if you perform this, the qubits, with the last qubits in this L and the first qubit in this R state are in a pure state, and this state decouples from all the other qubits. What are the generators for the other qubits? So we can use this list of things you have to do in order to update the generators. And for example, if you measure XX, then you see that it commutes with all of them. So you don't do anything to these generators. And it doesn't commute with it, so it replaces the generator. And you multiply another generator with which this generator does not commute by this. So you obtain here something like this, here obtain something like this, here obtain something like this. Here we use the fact that this is AME state. It means simply that you can have one Z and one X in a single column. These are generators for L state, and these are generators for R state. The next thing is to measure ZZ operator. So it doesn't commute with this, so we will replace this by ZZ operators, and the other operators with which it doesn't commute, we will multiply by this 1x. So here we have an operator with which it doesn't commute, so we multiply this by 1x and obtain this. Finally, we see that these qubits are in a pure state, so we can decouple these qubits, which just means you can cancel this row and these columns. So this is what is done, and what you have obtained is something like this. Okay, here is an example of, so this is what you obtain in this last equation are just of our new code. If you look at an example, it is something like this. Here are Pauli matrices which are in generators for some qubits. Here is some for example, absolutely maximally entangled state. Here is some other entangled state. You perform entanglement swapping on these two generators, update your generators, and you obtain some concatenation of quantum error correcting codes. Why it is important? So one is in quantum computation, of course. The other thing why it is important is because of quantum gravity. So now I would like to go to quantum gravity. So what you see, this is an artist view of hyperbolic space. So this is MC Escher circle limit, and you can think about hyperbolic space in the following way. Imagine that all this, let me call it square, are of the same size. So this is the same size as this is the same size as this. You cannot imagine this in Euclidean space, but if you have hyperbolic space, you can imagine this. This is very important because of the so-called ADS-CFT correspondence. So ADS-CFT correspondence is a very important thing in string theory and quantum gravity. And it says something like this. Imagine that you have gravity theory in anti-de Sitter space-time. On the boundary of the space-time, you have conformal field theory. So these are theory are duals to each other. So you can imagine what you calculate here in anti-de Sitter space-time, you can calculate here in the boundary of this anti-de Sitter space. It is better to forget now about quantum gravity and think about quantum error correction. So we will model space-time as an error correction code. It was done by these guys in 2015. These are so-called perfect tensors. So you can think of this as some matrices which act in the following space, in the following way. It is a map from some number of qubits into some other number of qubits, but the sum of these two qubits plus the sum of these two qubits in this case is 6. And if the dimension of this Hilbert space is smaller than this Hilbert space, and just acts like an isometry. So we can think about it that it encodes these two qubits into this form. If we look here, this means that it encodes this single qubit and this qubit. There should be one error. I have an error here. Yes. So here should be one qubit in. I know. This is also an incoming qubit. So these two qubits are encoded into these 4 qubits. Here, this qubits, and this qubits are encoded in this 3 qubits. And here, if it acts from higher dimensional spins into the lower dimensional Hilbert space, it cannot act as an isometry. So here is just the definition of isometry. Now you can use it to relate it to absolutely maximally entangled states. Absolutely maximally entangled states are just given in the following way. These are the coefficients of these tensors, and this state is absolutely maximally entangled.
It's always like that you can.
Yes, if these are perfect tensors, so these tensors act as isometries, then for each perfect tensor, from these elements of these tensors, you can construct a state which is absolutely maximally entangled.
Okay.
Here is a model of space-time as an error-correcting code. Think about it. You have a qubit, for example, here, and you will use this error-correcting code related to this absolutely maximally entangled state. So you encode this qubit here, and it is encoded in this qubit, this qubit, this qubit, this qubit, and this qubit. Go there. Here, you encode another qubit, and you have one qubit which was encoded here, and there is encoded here, and you encode it into what? Into 1, 2, 3, 4 qubits, so it still acts as an isometry. So this information will be contained here, the information about these qubits will be contained here, and so on. So we can look at it in the following way. the information about this, and this will go into these qubits, which I will cut here. Okay, and you can follow in the same way further. What you obtain will obtain ADS-CFT correspondence. So you have some information which is defined here in this anti-de Sitter space. So this I just read qubits, and it is mapped to the boundary.
What is time doing?
There is no time. If you would like to have time, you would add to here and another dimension. So I just look at some time slice. Why it is important? It is important for various things. And one thing which you can try to calculate is to calculate entanglement in quantum field theory. So let us imagine that I have some region of this boundary. And I have here some interval, for example, from this point to this point. How entangled are quantum fields on this interval with quantum fields on the complementary interval? You can calculate it, and people have done such a thing. But ADS-CFT correspondence gives you a very simple answer. If this boundary is one-dimensional, then the entanglement of this interval with the complementary interval is proportional to the length of the smallest geodesics connecting these boundary points in anti-de Sitter space. You can do this for higher dimensions, but then won't be, for example, if this is two-dimensional, then here you won't take geodesics, but you take area, and so on and so on. This is always the length of minimal geodesic, minimal area, and so on. Here it is shown how it looks for this example of an error correcting code. So, for example, the entanglement of these qubits from 13 to 20 with the rest of these blue qubits is equal to the length of this geodesic. So because it cuts two edges, it is equal to 2. And this is called Ryuta-Yanagi formula. This Ryuta-Yanagi formula, however, obtains some corrections, and it is only for some cases that it is equal to 2. So here I will give you an example. So the state on the boundary can be expressed in the following way. PAI are some tensors which encode these qubits which cut this geodesic and these qubits into these qubits. So the state is the following. Here you have one state, A are these qubits on the boundary and B are these qubits on the complementary. These are some tensors, and you sum over A. If you look at the entanglement of this and assume that this state is pure, sorry, not pure, but product, it is always pure. So this state is product, then you obtain that your state of the boundary looks like this. And because you have here some state I and some state Qi, and you sum over it, so the entanglement can be at most equal to the number of such state, because I denotes the qubits which you cut through this geodesic. Then you see that this entanglement in our case will be equal, will be upper bounded by the length of this geodesic. So this is the entropy. However, for a general state which is not pure state, there is some correction to this Ryuta-Yanagi formula. So this gamma is just the length of this geodesic, and this P is the number of qubits which are in one of these regions. So for example, if you cut something like here, so gamma is equal to 2 because you cut these 2 qubits, and here it is equal to 2 because you have 2 qubits in this region of anti-de Sitter space. And here is how the results looks. So if you have a product state and you cut your boundary between qubit 20 and some other qubit which you have on this axis. So for example, if you cut between qubit 15 and qubit 20, you will obtain that the entanglement is here. So this is if you put into the red qubits a product state. On the other hand, if into the red qubits you will put a singlet state, GHZ states, AME states. For a single state, you have singlet between 2 qubits. All other qubits are in product states. In GHZ, you use 6 qubit GHZ state. Here is 6 qubit absolutely maximally entangled state. So let me. So here is either single state, for example, between this and between this. Here you have GHZ state. So this is 6 qubit GHZ state between these red qubits, or absolutely maximally entangled state. You will obtain the following correction to this Ryuta-Kayanagi formula. Ryuta-Kayanagi formula is for this product state. You see that the entanglement can increase. So now I would like to go to shortly to another topic. So what is the response of absolutely maximally entangled states to noise? Let us suppose that I will take some state and send each qubit for identical quantum channel. We'll consider 2 channels. One is the polarizing channel. So you have this 5 qubit absolutely maximally entangled state, and you send each qubit through the polarizing channel, or you send each qubit through the dephasing channel. What happens between entanglement for each cut? So it happens the following way. If you set each qubit, you can calculate some entanglement measure. Entanglement measure for higher dimensional Hilbert spaces, which is easy to calculate, is logarithmic negativity. Here it is defined by this equation. And it is an upper bound on distillable entanglement, which has operational meaning. You can also use something which is not entanglement measure, but which is lower bound on distillable entanglement, and it is coherent information. From coherent information can be defined either by this equation or by this equation, and they are not equal. So it is better to go the lower bound, which is higher, so you should take greater of this coherent information, and greater coherent information is this, which subsystems contains more qubits. So for example, a subsystem B contains more qubits, then this coherent information will be greater than this. And here, how it looks. So here is the bipartition of 1 qubit versus 4 qubits, and you can have 5 such bipartitions. So you can have bipartition of 1 qubit versus the first qubit versus the next qubit, the second qubit versus the next other qubits, the first qubit versus other. And what happens, the entanglement is the same across any bipartite cut. So not the entanglement was at the beginning for this bipartite cuts the same, but it also decayed in the same way, which is not obvious. This is not obvious because the state is not permutationally invariant. And I will give you examples of AME states where this is not the case. Here is 10 bipartite cuts of 2 qubits versus 3 qubits. Here you also see that the entanglement decays in the same way. Here are just results for coherent information. You just see that it behaves similarly to logarithmic negativity. Here it is done for the dephasing channel. It also decays the same. Here is also for the dephasing channel coherent information. It also decays the same. And now let us suppose that I will take another AME state. What absolutely maximally entangled state I can take? I can take any unitarily equivalent absolutely maximally entangled states is I will act only with unitary with unitaries which are local. For dephasing channels, it happens that local unitary operations commute with our channel. So it just means that the entanglement doesn't depend on what state you will choose if you send it through the depolarizing channels, because entanglement measures are invariant with respect to local unitary operations. However, for dephasing channel, the entanglement can depend on which absolutely maximally entangled state you use. And here we have taken such a state which is locally unitarily equivalent and calculate once again entanglement measure. And what you see that logarithmic negativity decays for different bipartite cuts. So for some AME states, you can choose AME state in such a way that entanglement decays in the same way, but on the other cases, you, for example, see that here entanglement decays much stronger than, for example, here. And similar results you will obtain for coherent information. Okay, similar behavior is also for 6-qubit AME state. Because I am out of time, I will skip this, but I will be happy to talk about this. And I will go just to the conclusions. So conclusions are the following. We showed how to determine stabilizers and logical operators of quantum error correcting codes corresponding to absolutely maximally entangled state. We applied this method to concatenation to quantum error correction codes. We calculate corrections to Ryuta-Kayanagi formula for simple holographic code. And we analyze the effect of noise on qubit absolutely maximally entangled states. Thank you very much for your attention.